I'd like to start by thanking the organizers for organizing this wonderful event and for the opportunity to present my work here. And of course, thanks to everyone in the audience for showing interest and coming here to listen to my presentation. This work, I'd like to start by saying that this work is a paper that was published in the Journal of Machine Learning Research last year, and it's a work in collaboration with a wonderful team of collaborators. The title that I chose for this presentation is actually the title of the workshop version of this work, which was presented 1 year before at the workshop in NeurIPS 2020. And in a nutshell, this work is about learning and certification strategies for neural network classifiers based on PAC-based bounds. So I'll give you a quick overview of my presentation. I'm going to give a very quick run-through statistical learning. They told me I have a captive audience here, so I'm going to use it in order to pitch for statistical learning a little bit. And then I'm going to talk about PAC-based bounds, which is the main thing that we used for these learning and certification strategies. Because the name PAC-based begs for a little bit of explanation, I'm going to say something about the similarities and the differences between Bayesian inference and PAC-based bounds. Then I'm going to go through the learning and certification strategies themselves for neural network classifiers and a quick highlight of the main results. So let's get started. This is my one-slide summary of the statistical learning setting. You have an algorithm that receives data, and then the algorithm outputs some learning model. Typically, the learning model is mapped to a set of parameters. And so think of an algorithm as receiving data and then producing parameter values. So the data, this is a setting of supervised learning, so the data consists of inputs and labels. For the training data, we have inputs and correct labels. And then you have like weight pays, which corresponds to the parameters of the learning model. And those weights are mapped to prediction functions that will be used once training. The prediction function will be used to make predictions in the future. Call it classifications, assigning labels to new inputs in the future. And in order to make learning possible, some assumptions need to be made on the data, something that connects, for instance, training data with testing data and with future unseen data. The assumptions under which we work is the statistical learning assumption of IID data, independent, identically distributed data points. And two performance measures that are like very well known, classical, are the empirical risk, which means for classification, calculate the average error over a finite number of examples. But the true measure of interest that we would like to address is what we call the risk, which is the corresponding, like the population counterpart of that sample average. So think of the contrast between those two. Sample average is the empirical risk. The true measure that we would like to know is the risk, which is at population level, beyond any finite sample. The empirical risk, so the average over a finite number of examples, gives rise to a classical learning paradigm, which is called empirical risk minimization. It says, find a set of parameters that minimizes the empirical risk. It's a very classical learning rule. Of course, it depends on the choice of loss function. For different learning problems, different loss functions make sense. For classification problems, the 0-1 loss is a loss that makes more sense. Unfortunately, for optimization, especially gradient-based optimization, it's an untractable loss because it gives piecewise constant optimization objectives. So typically, surrogate losses are used, the squared loss, the cross-entropy loss, some sort of loss that is amenable to gradient-based optimization. I won't say too much more, except that there is a penalized counterpart of ERM, which tries to solve some of the limitations of ERM, such as instability and overfitting. Moving on, the test set error is the most commonly used measure of performance throughout the community. Which it goes by find a set of parameters. However, you find your learning procedure to find a set of parameters, then evaluate the average error on a held out set of examples that were not used for training. However, I'd like to point out that the test error is just a point estimate of the true error. It is not the same as the true error, and the quantity of interest that we would like to know about is the true error itself. A bit better than using the test error is using confidence bounds, and this is what statistical learning aims to produce, confidence bounds. These are high probability bounds. Sorry about that, high probability bounds that typically say that with high probability over random samples of a given size, the true loss, the quantity of interest, is bounded by the empirical loss, something computable on a finite number of examples, and some correction term depending on parameters. And those bounds, I won't say too much about them, but I want to say how they are used typically. There are two typical uses of confidence bounds. One is for certification of risk, which means if you find your favorite learning procedure, now you can use a confidence bound to plug the output of that learning procedure into the confidence bound and certify the risk of that prediction, of that predictor. And another use, which is explored not as much as the first one, is bound minimization, which means turn the confidence bound itself into a learning objective. And this is what we are going to do. I'm going to come back to this, because this is one of the main things that we did in this work. Moving on, I'm going to say a little bit about PAC-based bounds. They address something different than the classical setting in that the output of the learning algorithm is not a fixed setting of parameters, but it is a probability distribution over parameters. So think that the algorithm takes data, and then the output of the training process should be a distribution over parameters. The prediction rule that I'm going to address is a randomized prediction, which means after training for future predictions, for every new input, freshly sample the parameters from the distribution output by the algorithm. And then for that prediction rule, the risk measures that make sense are like the classical empirical risk and the classical risk, but lifted to the space of distributions over parameters. So that means the loss of a distribution and the empirical loss of a distribution are the expectation of the classical loss and empirical loss, where the expectation is with respect to the distribution over parameters. This is just a quick picture of what the classical PAC-based bound looks like. It tells you that the loss of a distribution, an uncomputable term, if you don't know the data generating distribution, it is upper bounded by the empirical loss, computable from data, and some other terms, KL divergence between the distribution and some fixed prior distribution. Won't go too much in details, but credit to McAllister back in the late 1990s, where this PAC-based bound was first proposed in a little bit of a different form. It's been refined later. The PAC-based KL bound is a little bit different, and I just want to mention it later for the learning strategies and the certification strategy especially. It's a little bit different in that the quantity upper bounded is the KL divergence, the binary KL divergence between the empirical loss and the true loss. So think of this actually as two Bernoulli parameters, an empirical Bernoulli parameter and a population level Bernoulli parameter. So this is the KL divergence between two Bernoulli distributions, and the upper bound is in terms of things like the KL between the two distributions and sample size and whatnot. Moving on, here are two more PAC-based bounds. One that this is one of the contributions of our work. This is one of the things that I did while working on this project. Realized that one can find a new kind of bound, and why it is interesting, well, we didn't have any reason why to say that it was interesting beforehand. It was found by pretty much the same procedure as this bound that was known before called the lambda bound, except that it used one less inequality along the derivation of the bound. That was interesting in itself. If you are into analysis, the less inequalities that you use, the tighter the difference between the left-hand side and the right-hand side of the inequality. And later I will tell you what happened in the experiments also, why like, after the experiments, why this bound was interesting. Moving on. Just like the classical generalization bounds, two typical ways to use PAC-based bounds. For certification, which means use your favorite algorithm as a learning procedure. So find parameter settings by like the algorithms that you prefer, empirical risk minimization, any regularized form, Bayesian procedure or not, like use really your favorite procedure, and then use one of the PAC-based bounds to plug the distribution output by your learning procedure in order to calculate a certificate. The other possible use is use the upper bound as a learning objective, which means declare that your learning rule is finding a distribution that minimizes that function. So in the work that I'm presenting today, we use actually both of them. The learning objectives were derived from PAC-based bounds, and the certification was done using a PAC-based bound as well. Just a quick thing about the difference between Bayesian inference and what are called PAC-based bounds. In Bayesian inference, you postulate a prior distribution over parameters, and you postulate a family, a model family for the data generation process, and then you construct this update rule that says once data comes in, there is a likelihood factor that updates the prior in order to produce the posterior distribution. So there is a very there is a fixed relationship between posterior and prior in Bayesian learning, and it depends a lot on the likelihood factor. I want to give very fair credit to it. Gives very nice principled approaches to interpret learning procedures. For instance, think of maximum a posteriori learning. The Bayesian rule gives you a way to via maximum a posteriori learning, gives you a nice, sensible way to make sense of regularized empirical risk minimization with a choice of, for instance, Gaussian distributions. Then you get L2 regularization of the empirical risk, and other choices are possible. With Laplace distributions, you get L1 regularization of the empirical risk. And the thing that I would like you to notice also is that there is a balance in this form of the update to produce a posterior. There is a balance between prior distribution and likelihood factor. So Bayesian learning rules tend to do a balance between fit to prior and fit to data. There are some extensions of the Bayesian, of the classical Bayesian setting. They are called generalized Bayesian approaches. For instance, the first that I knew of is you can temper the likelihood by an exponent. In the maximum posterior setting, it corresponds to controlling the amount of regularization informed by the prior. Or you can use a function which is data dependent and parameter dependent, not interpreted as likelihood anymore, but some function that you're going to introduce as a factor of the prior in order to produce a posterior. Here is a very good reference if anybody was to check, and I'm always happy to be contacted later for any details and discussions, any follow-ups. So that's generalized Bayesian, still very closely connected to the classical learning rule in the sense that there is a strict relationship between what are called the posteriors and the priors. In PAC-based learning, there is no update factor. So PAC-based bounds are a little bit different from what is called Bayesian inference. There is no factor connecting posteriors and priors. In fact, I should tell you right away, the name posteriors and priors and then Bayes in PAC-based, it just got introduced in the late 90s by some work and it's stuck in the literature. I don't think anybody is going to change it. But these are frequentist bounds. There is nothing Bayesian about PAC-based bounds. You can use them to certify your Bayesian procedures, that's fine, but don't interpret it as Bayesian. So that's the difference. They give a lot of more flexibility in the choice of distributions because there is no strict connection between posteriors and priors. There is no equality and factors connecting these distributions. And the similarity is that they still kind of try to achieve a balance between fit to data and fit to prior. I'll say more about that in a moment. So moving on to the learning and certification strategies. So far, so good. Just checking with the audience, are we still all on board? So let's go to the learning and certification strategies. Again, this was all reported in this paper, a little bit of self-advertisement. Credit to Maria, who was in charge of the implementation of the experiments, and John and Chava were kind of like the senior collaborators. And credit to some works that were very influential to our work. There was a 2015 paper, Weight Uncertainty in Neural Networks, that explored learning distributions over neural network weights. It used a Bayesian inference approach, actually a variational Bayes, so it's still a little bit more general than Bayes. And they introduced an optimization algorithm that they called Bayes by Backprop. This was one of the main things that got started the project, our project. We kind of borrowed the form of the name. I'll tell you what our algorithm is called in a moment. Timan et al. This 2017 paper, they introduced the PAC-based lambda bound. And I give credit to them because we used the PAC-based lambda bound as one of the training objectives. Although they did not apply it to neural networks, they applied it to support vector machines. And then Zugati and Roy, anybody who works on like deep learning theory probably has heard these two names. They demonstrated non-vacuous bound values for over-parameterized neural network classifiers in that 2017 paper that was called Computing Non-Vacuous Generalization Bounds for Neural Networks. Many more things in the title. So credit to those works, and moving on. In a classical neural network setting, what you want to do is use available data in order to achieve two things. One is learn a setting of the connection weights of the neural network architecture, and the other one is certify the performance of that neural network with that setting of the weights. The classical approach is to use data splitting, so use part of the data as training data, and then held out some data in order to evaluate the test errors post-training. What I want to do is that I like to think about a way in which you can take advantage of the whole available data in order to do both things simultaneously, learning and certification. And this is one of the things that we try to do in this work. What we call probabilistic neural net, they also have also been called stochastic neural networks in the literature. This is the same thing. Learn distributions over neural network weights. And then you want to use the data for like learn the right distribution over network weights and then certify the performance of the classifiers defined by those distributions. There are variational-based approaches to do that. One of those is the algorithm called PAC-based by Backprop that I just mentioned from that 2015 paper. Our approach was to turn PAC-based bounds into learning objectives, and our optimization algorithm, PAC-based with Backprop, I'll explain why in a moment when I show you the algorithm, and we use both. We use the PAC-based bounds for both for learning and for certification. How am I doing with time? 1 minute. Good. This is my algorithm. Ask me about it when you want details. It's pretty much reparameterized gradients applied to the objectives derived by PAC-based bounds. This is a certification strategy. Blah, blah, blah. This is what I want you to take as take-home message. This picture is like one of the main messages of our paper. So the top two frames are fully connected network architectures. The bottom two are convolutional neural networks. The two frames on the left used prior distributions that don't depend on the data in any way, and the two on the right use prior distributions that were learned from the data. And in all of them, the dashed horizontal line is the test error of empirical risk minimization, the classical way to train neural network classifiers. And each of the bars, everywhere, each of the bars, the bottom part, shaded part, is the test error of the corresponding classifier found by the corresponding method labeled at the bottom, and the total height of the bar is the value of our certificate. Think of a certificate as a promise. On any data of the same distribution, the error, that we don't know it, but we promise that it won't be larger than this amount. And everything gets lower and lower. We want to point out this little one over here. FQuad, that training objective that I mentioned, learning the PAC-based quadratic bound, gave classifiers with a test error that was pretty much there, very close to the test error of plain empirical risk minimization, about 1% error, that means 99% classification accuracy, and with a promise of performance that on the same data, this algorithm will not have an error of more than 1.5%. We think that was a very exciting message, a very tight, a very close value of the generalization bound, valid at population level, and the rest of the picture is comparisons with all the other methods. There were other things that were exciting in this work. One last that I want to mention is the risk certificates calculated by our certification strategies were very strongly correlated with the classification errors. So this suggested these things can also be used for model selection. And that's another thing that we hope that can be explored more in the future. Thank you very much.